My pleasure to be with all of you today. Thanks for coming. And I want to talk to you a little bit about IRIS technology. IRIS technology, I think probably most of you are familiar with IRIS tubes. This is a technology for documenting reducing conditions in soils. It's been around for about 15 years. It really emerged from the work of Byron Jenkinson at Purdue working on his doctoral dissertation. But these are half-inch PVC pipes coated with an iron oxide paint. And the way they work is we put them in, we make a pilot hole into a soil, and then we follow that. We drop in our IRIS tube, which is this PVC pipe coated with iron oxide paint. As the soil becomes anaerobic, or if it's already anaerobic when the tube goes in, the microbes, as they're oxidizing organic material, start looking for alternate electron acceptors. They find the iron on the tube, and as they begin to put electrons on there, the iron gets reduced, it becomes solubilized, it gets stripped off, and then as these come out, we can quantify it, and that tells us something about how reducing this environment is. They're easy to use. The practitioners love them because they're pretty simple and they integrate over the period of time. Normally, these go in or installed for about a month. That's sort of the standard protocol. And normally, we install about 5 of these because redox processes and properties in soils are pretty variable. Do the same thing if you're making redox measurements with electrodes. You have to use replication. So then when they come out, then we try to make assessments, quantify this. If you follow the protocols of the National Technical Committee for Hydric Soils, that is, if you're trying to meet the technical standard for hydric soils, they say we look in the upper 30 centimeters of the soil, which is sort of the upper part, and you identify that zone on the tubes that has the maximum removal within a 15 centimeter zone, and then you quantify that. And if that's more than 30% removed in a majority of the tubes, then that meets the technical standard. There are some alternate ways to think about this. Some earlier work that we did showed that if we have between 20 and 25% removal of the coatings within a 10 centimeter zone, that we got about between 90 and 100% likelihood that it really is reducing. So there's different ways to approach this. But the real question in dealing with this is, how do you quantify this, right? Because these are three-dimensional, cylindrical shaped devices, and so it's a little bit challenging to get some data that's useful. So the way we always started with this was using visual estimations. And you spin the tube around, you look at it, you compare it to standard charts like we do for making estimations of redox features in soils or estimating coarse fragment and soil profiles. And the bottom line is it's not very accurate. We did some studies, and the average error was absolute error of 9%. Some people are better, some people are worse. I won't mention any names, but there was one individual in the study that his average error was 20%. But the best was about 5. So anyway, there's a lot of error associated with it, and so another approach that people used was photographing the tubes and then rotating the tubes 120 degrees, compositing these together, and that gives you a better image to work with. But you still have some things with distortion around the edges. You get shading. People will try to apply image analysis to this, and those kinds of shading differences interfere with your ability to get it, and it's pretty time-consuming to do all that work in Photoshop. And we've done a lot of it. And I guess if you have a student doing it, you can spend all their time you want, but it takes a while. In our lab, we actually developed a flatbed scanner that we took a saw to and epoxied some. Let's see, there is a mouse in here somewhere.
The trackpad.
Oh, just the trackpad. Okay, so. Flatbed scanner with these little posts on here that we epoxied into the scanning head, so that as the scanning head moves, it rolls the tube and unwraps the tube, keeps it directly above the scanning head as it moves. It works great, but the limitation is you've only got an 8.5-inch maximum scanning width, so if you want to do a whole tube, you got to do it 2 or 3 times and then put those together. And you can come up with some pretty nice images, and it actually gives you a nice unrolled 2-dimensional image, but to my knowledge, I think I'm the only person in the country with one of these devices. You can make them. I actually it took me 3 machines with the saw in order to get one that worked, so they're not too expensive. These are like $150 or something, probably cheaper now, right? And then, so our sort of go-to method at this point with the tubes is to take just a Mylar grid, wrap it around the tube, mark the places where it's been removed with a Sharpie, then you count it, And the accuracy that we've gotten on this, we've done some studies and comparisons, it's relatively accurate. You get plus or minus about 3% with different operators, but you got to admit this is pretty old school, right? In a digital age, you know, marking grids and counting and all that stuff. And it's also pretty time consuming. So this is all to say that, you know, in the use of iris tubes over the last decade, that they've really sort of moved into this, I don't know if it's mainstream, but certainly a lot more people are using this. One of the issues is how do you get the good data out of there. But there's been also a number of other issues that have emerged with iris tubes. One is you can have abrasion on the tubes, especially if you're installing these into sandy soils or dense soils as they go in. Even though you make a pilot hole, you get some abrasion and removal, and that sort of gets counted often. There's also potential for abrasion and scratching as you transport them. This is a picture of the device that we use to kind of keep our tubes isolated from one another when we carry it in, but it's pretty bulky, it's pretty heavy, it's effective. I don't know if anybody else is doing this or not, but that's one approach, but that's a concern. And then there's also just issues about storage volume, whether before you deploy it, you got them sitting in your office or lab, you got 100 tubes there, or you bring them back after they're used. And then there's also issues associated with expense of transport, the weight of these things. And then there's just sort of general environmental sustainability issues. You know, you end up with a bunch of these used tubes. They can't be recycled. We tried to get the coating off to reuse them. You really can't do that. And so what are we going to do? Well, here's our proposal, what we're calling the new iris technology. And it's using plastic films, vinyl films. And the idea is not new, because especially with the issue of this three-dimensional, I mean, people have said all along, you need a flat surface, right? So you get a film or a panel or something like that. And a few folks have done this. We've done it ourselves. And at the Houston meetings, Paula Gale reported on, you know, trying to do this. A couple of months ago, Karen published a paper. We're using panels, and you know, the panels are big and heavy, and the films are. It's hard to get a film in with, you know, how do you, without digging a hole and backfilling. But it's probably, the way it's been done is probably useful or usable in research. It's not very applicable to sort of a broad scale. So here's our plan for how to address this. And I actually have some show and tell up here at the end of the session. You want to come up and see what these look like. But we start with a 10 mil vinyl film. It's a rigid vinyl film. We paint using a foam brush. Similarly, we paint the coating on. The dimensions are essentially the same dimension as an iris tube, right? 50 centimeters high with the line. And then we cut these into 3-inch strips. And this is great. You know, this is about the same size. But the question is, you know, how do you get them in the ground, right? That's what everyone wants to know. How do you get them in the ground? So here's how you do it. So you first have to get them inside a clear polycarbonate tube. And the way you do that is you wrap the film around a smaller tube, and then you can slide it in. Slide in the tube with the small tube, and once it's in there, you let go, and the film expands. The smaller tube pops right back out. So here's what the films look like. With the empty tube, there's an important little hole punched in the bottom of this film we'll come back to, right? So here's after you roll them in. This is the way they look. This is the way they're loaded. This is polycarbonate, right? You know what they make out of polycarbonate? Bulletproof glass, right? Lexan. So this is indestructible. You get these preloaded. This is the way they're sitting as you're heading to the field. You can throw them in the back of your truck. They're going to bounce against each other. They're not going to get scratched. They're sort of very well protected. So this is what you do when you get to the field. Once you get them loaded into the tube, you make a pilot hole just like we did before. It's going to be a slightly larger hole because these are 1-inch tubes. So we have a 1-inch hole instead of a 7/8-inch pilot hole. Then we take what I'm calling a push rod. It's a 4-foot long rod, has a little hook on the bottom of it. And you slide this hook down the tube so that it hooks through this little hole in the bottom of the film. Then you grab hold of both the rod and the tube, and you slide these in together. You know, it's got to be hooked into that hole before you get it into the ground. It stays in it all the way down. Once it's in there, you grab hold of the rod, keep that in place, and you can slide the tube right out. And in the process, you leave the film in place, and then you can pop out the rod afterwards, right? Great in theory, just to prove that we can do it in reality. Well, in just a second here. So from a top plan view, there's the pilot hole, there's the tube with the film on the inside. Then when you slide the tube out, the film expands, and you get the nice contact up against the side because it's this rigid, semi-rigid film, right? So here's Evan making a pilot hole for one of these, and then you grab the rod and the tube hooked into place. You start to slide it down. You push it right into the ground just like you would a normal tube. Then you grab hold of the rod. You begin to slide the tube out until it pops out, and then you pull the rod out, and you've got your films installed just like a tube. Magic. How do they work? We have some preliminary data. These were installed in a wetland last spring, and this is a saturated wetland. It actually had water very close to the surface during the month, but it was a little early, it was a little cold. The point is that there's no statistical difference between the amount that was removed from the tubes and the films. There's just a lot of variability in here, and it's also very possible that the slight increase is due to abrasion. If you look at these tubes, you can see there was abrasion on some of these tubes, which you don't get on the films because they're protected when they go in. We also experimented with some manganese coatings. If you want to hear more about manganese coatings, just wait about 45 minutes. I'll give you a 5-minute blurb about a poster coming on later today. But again, no statistical difference in the amount of paint that was removed from these between the films and the tubes as well. So we feel like we've addressed some of these issues related to data acquisition, abrasion, but there's still these questions about storage volume, weight and size, environmental sustainability. So what about storage? It takes about, if you store 40 tubes, closest packing, most efficient way to store these, it still takes 9.5 liters of volume. By comparison, 40 tubes takes about a half a liter, 5% of the storage volume. In terms of the weight, if you want to ship 30 tubes, it weighs 8 pounds. 30 films weighs about a pound. Maybe that's not a big deal, but I had a colleague in Spain, and twice I had to ship a bunch of iris tubes to Spain, and to ship 20 or 30 tubes, I spent $100 just to get the tubes over there. Maybe in the cost of research, that's not a big deal, but so it's pretty minimal. And then there's these issues of general sustainability, right? This is a shot in the corner of my lab, and this is 350 tubes or so sitting there, and as I tell people, there's only so many wind chimes you can make out of these things. I thought maybe you could cut them into small, make Christmas tree ornaments or something. I don't know what the market would be, but the folks that we were talking that were using them, they just, they feel bad having these sitting around. They go into a landfill, or you try to recycle them, but you can't reuse them because there's not an easy way to get the paint off. So we think that we've hit all these issues by this new technology, and so we conclude that we have a system now that we think that we can use for pretty easily deploying these flat iris films, we're calling them, and that makes it relatively easy to get a nice two-dimensional image. It'll improve potentially image analysis approaches to getting those data. The preliminary work that we've done shows that they perform essentially the same as the tubes. Not surprising. Same materials, are both vinyl, both PVC. And it also addresses a number of these other issues of concerns about abrasion and scratching, storage volume and weight, and the general sustainability. So we think this is the new iris, the next generation. So with that, I'll be glad to answer any questions.